Welcome to This Explainer. Today, we're stepping back into the fascinating evolutionary history of computer memory management. Together, we're going to build a step-by-step understanding of exactly how early computers learned to juggle multiple programs at once, and more importantly, how those foundational concepts literally built the devices we use every single day.
Let's kick things off with a pretty profound thought from the 18th century writer Samuel Johnson. He said, "Memory is the primary and fundamental power without which there could be no other intellectual operation." Now, what's really fascinating here is that while Johnson was talking about the human mind, this exact same principle applies directly to computers. Just like human intellect, a computer's true power, capability, and performance rely completely on how effectively it manages its memory. I mean, if a system can't organize its thoughts, so to speak, it simply can't function.
Okay, here is our roadmap for today. We'll start with an introduction to main memory, walk through 4 foundational allocation schemes, tackle the fragmentation problem, compare first fit versus best fit, look at a real-world application with compaction, and finally wrap up with essential key takeaways. Section 1. Introduction to main memory. Let's dive right into our first core concept to understand exactly what the operating system's memory manager is dealing with. For decades, a computer's speed wasn't just about the processor. It directly depended on 2 crucial things: how much RAM, or main memory, was physically available, and how cleverly the operating system optimized it while processing jobs. You could have the fastest CPU in the world, but if your memory manager is inefficient, the whole system just grinds to a halt. Main memory is the workspace where all your active data and instructions absolutely must reside in order to be processed. Section 2. 4 foundational allocation schemes. Let's explore the chronological steps computer scientists took to solve this RAM bottleneck. We're looking at single user, fixed partitions, dynamic partitions, and relocatable dynamic. These 4 schemes represent an evolutionary narrative arc. As we go through them, you'll start to see a pattern. Each system was basically invented to solve the critical failure of the one that came before it. We start simple and gradually add complexity to gain efficiency. So picture this. It's the late 1940s and 50s. This is our first step, the single-user contiguous scheme. One entire program was loaded into a massive, undivided memory block. The operating system sat at the top, and the user's program just got the rest. But there were massive limitations here. The job had to be loaded in its entirety, and it had to be completely contiguous, meaning stored in one totally unbroken block. If the program was even 1 byte too large for the available space, no way, it simply could not run. Plus, it didn't support multi-programming. You couldn't run 2 jobs at once. For business machines costing hundreds of thousands of dollars, letting only one person run 1 job at a time was frankly a total deal breaker. Well, to stop wasting all that time and space, scientists invented fixed partitions. Think of them like pre-built static bookshelves. By sectioning off the memory, multiple jobs could finally run simultaneously. This was the birth of early multi-programming. It was a real game changer. However, there was a catch. Because these partitions were static, they were rigidly set by the computer operator in advance. If you had an unexpectedly large job arrive and it didn't fit on your pre-built shelves, you literally had to shut down and restart the entire system just to reconfigure the partition sizes. Multi-programming also introduced a brand new danger: partition intrusion. With multiple programs sitting side by side in memory, what prevents one program from accidentally reading or overwriting another program's data? The clever solution was the bounds register. This hardware register stores the highest or lowest legal memory address a specific program is allowed to access. So if a program tries to cross that invisible boundary, the system instantly catches it, resulting in a fatal application error and immediate termination. Boom, crashed. Section 3. The fragmentation problem. Moving from fixed partitions to dynamic partitions, where jobs are given exactly as much memory as they request the moment they load, solved that rigid bookshelf problem. But it introduced a new enemy: fragmentation. To truly understand dynamic memory allocation and its pitfalls, let's imagine you manage a super busy library. There's a continuous stream of people returning and checking out books of all different sizes. The books are the incoming computer jobs. The shelves are your memory partitions. And taking the time to completely rearrange the shelves to fit more books efficiently, that's what we call compaction. Keep this analogy in mind as we look at how our library shelves get messy. First up, we have internal fragmentation. Going back to fixed partitions for a second, This is basically like putting a tiny paperback book on a massive oversized shelf. Because that partition is assigned exclusively to that one book, all the extra empty space on that shelf is technically considered occupied by the system. It is completely unavailable to any other waiting jobs. It's totally wasted. It's fragmented internally.
On the flip side, we have external fragmentation. This is the curse of dynamic partitions. As jobs finish and leave the system, they free up their exact requested space. Over time, as new books come in and old books leave, you get these odd-sized gaps of free space left over between the busy blocks. These gaps might add up to a lot of total free memory, sure, but because they're broken up into tiny individual fragments, they're just way too small for any new incoming jobs to actually fit into. Section 4. First fit versus best fit. Let's see how this builds our next challenge. With all these fragmented gaps of free space scattered around, how on earth does the memory manager decide where to place a newly arriving job? System designers came up with two primary algorithms. First fit simply searches the memory list from the beginning and grabs the very first available space large enough to hold the job. It's incredibly fast, but it tends to waste larger blocks of space early in the memory list. Best fit, on the other hand, searches the entire list of free spaces to find the tightest possible squeeze, the block that will leave the absolute smallest amount of wasted space. This maximizes memory efficiency, right? But it slows down the system because it requires searching the whole list every single time. Plus, best fit often leaves behind tiny, practically unusable fragments of memory that we call slivers. Section 5. Real-world application, compaction. So, how do we actually clean up all these unusable fragments and slivers in the real world? How do we reclaim that wasted space? Well, using the fourth evolutionary scheme, relocatable dynamic partitions, the operating system performs compaction. You probably know this from the real world as defragmentation. Imagine a scenario where we have external fragmentation. There are empty gaps of unused memory, but none are big enough individually to hold a waiting job that needs, say, 84K of space. So the system takes action. It physically shoves all the busy blocks together. It compacts them, gathering all those empty gaps into one massive 96K block of clean, contiguous space. Now, that waiting job easily slides right in. But wait, compaction is a severe overhead process. It is absolutely not free. To compact the memory, the system must literally pause the entire library. No other processing can happen. It then moves the programs so they're contiguous. Most importantly, it has to meticulously update every single internal address reference to reflect the program's new physical location, all without accidentally changing the actual data values or instructions inside the program. Think about it. If it messes up a single address, the program will crash or reference the wrong data entirely. To safely pull this off during a move, the OS uses a brilliant piece of hardware called a relocation register. When a program is shifted down the memory block, this register calculates exactly how far it moved. It stores the exact mathematical offset needed to shift the job's internal addresses to their new physical location. Whenever the program tries to access memory, the system instantly adds the value in the relocation register to the request. This ensures the program always finds its data perfectly without breaking a sweat. Section 6. Essential key takeaways. We've covered a lot of evolutionary ground today, from single-user limitations all the way up to dynamic compaction. Let's wrap up this explainer with a rapid-fire summary of the absolute most important points you need to remember. Despite their incredible evolution over the years, all four of these simple schemes strictly mandated 3 golden rules. 1. An entire job had to be loaded into memory. 2. It had to be stored in one completely contiguous block. And 3, it had to stay in memory until it was completely finished. These 3 rules severely restricted the maximum size of any software. A program could simply never be larger than the biggest single partition of available main memory, which leaves us with a totally fascinating puzzle to end on. If these foundational systems rigidly dictate that you can only run programs smaller than your total RAM, how does your modern computer or gaming console play a massive 100-gigabyte video game when you only have 16 gigabytes of main memory installed? The answer lies in breaking those 3 strict rules we just talked about, which open the door to modern virtual memory. But that is a story for our next explainer. Keep this question in mind, and thanks so much for learning with me today.